Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to the concept of equivalent capacitance. After watching this video, hopefully you'll understand what equivalent capacitance means and how it's calculated for both series circuits and parallel types of circuit combinations. So, for now, I'd like you to focus on this picture on the left. And what we're looking at is a pair of capacitors connected to a battery which has some sort of voltage source, delta V. And we have a switch in the circuit. Two capacitors with different capacitances, C1, C2, and this is referred to as a series circuit. Basically, you know, if it's in line, so to speak, it's a series circuit. And the next circuit we'll look at is going to be a parallel circuit. All right, so now imagine the switch is closed. Our battery is going to push charge through the circuit. So basically what's going to happen is it's going to draw electrons from this charge, from this plate, leaving this positively charged, and coming on over here now, it's going to push electrons onto this plate. Now, charge, you know, has to move through the circuit in a way that the same amount of charge that moves through here has to move through here, has to move through here. You know, it's a lot like a water hose. If I have a water hose, you know, and I have 10 gallons go through here, 10 gallons has to move through here, 10 gallons has to move through here, 10 gallons has to move through here. Once it's a steady state situation, meaning that, you know, after the hose is filled up with water. Well, the electrons, you know, the charge in a wire is everywhere, right? The wire is already full of charge, so to speak. There is no filling it with charge. We're just getting the charge to move through the wire. Similarly, like here, it's, you know, the hose is already filled with water. Now we're just moving water through the hose. So if 10 gallons moves through here, 10 gallons moves through here, 10 gallons moves through here. It's the same thing with this circuit. So whatever charge moves through this point, the same amount has to move through here, same amount has to move through here, right? So what that means basically is this. If I end up with a plus Q on this plate, we have to have a minus Q on this plate. If I have a minus Q here, I end up with a plus Q here. So we have charged capacitors now. Now again, the net charge on that system is now 0, but that's when we talk about the charge on a capacitor, we're talking about a charge imbalance. So we have a certain charge on this capacitor. I'm going to give it a name for a minute, Q1. Right? We have a certain charge here. I'm going to give it a name, call that Q2. Now, I'm going to go back and revisit that argument. It's very important to understand that if I pick a couple sections of this wire, like here, here, and here, the same amount of charge has to move through each section. I can't have 1 coulomb of charge move here, and 2 here, and 3 here, or anything like that. If 2 coulombs goes past this point, 2 coulombs has to move through that point, 2 coulombs has to move through that point. So, that means that these charges, Q1 and Q2, they have to be the same. So I'm going to go ahead and just erase the subscripts on them because the charges in this example have to be the same. Now, the plates now, each one of these has a voltage across it. So I'm going to call the voltage across this plate V1 and the voltage across this one V2. And again, imagine, you know, to talk about the potential difference here, we've got a positive charge on the left, negative charge on the right. So now we have electric field lines between these plates. And those electric field lines would point to the right, because electric field lines always point away from positive charge towards negative charge. And remember, potential difference is field strength times distance. So there's now a potential difference across each of these capacitors. Right? So I'm going to call this potential V1 and this potential V2. All right, equivalent capacitance. The idea behind equivalent capacitance is this. It would be nice if we had kind of a mathematical way of replacing this pair of capacitors with a single capacitor that's mathematically equivalent to the pair. Right? So that's the idea behind equivalent capacitance. Now, why would we want to do that? Well, we've got 2 capacitors on the left, but only 1 on the right. So the right-hand circuit is just a simpler circuit to deal with than the left-hand circuit. Now, as far as how do we mathematically do that? Well, first I'm going to talk about voltage a little bit more. Let's go back to this original picture. Let me get voltage symbols over here. Remember that conductors are equipotentials. So what that means is this plate This is all one potential from the battery terminal all the way to here, because this is all conducting material. Now, on the other side of the capacitor, this is all conducting material as well here too. So this is all one potential. So I'm going to color code that orange. And then the other side of this plate here, this is all one potential all the way to here. I'm just going to leave that black. Now, notice that the voltage across the battery, red to black. Get this kind of out of the way here. And notice capacitor 1 here, red to orange, and then orange to black. But when you look across the system, we're red to black. So the potential across both of these, which I'm going to call just delta V for a minute, is equal to the potential across here, red to orange, which is what I'm calling potential 1, plus the potential across here, which is what I call potential 2. So the potential differences across these capacitors add to the potential difference across the battery. All right. Now, from how capacitance is defined, all right, capacitance is charge over voltage. I can rearrange this equation quite easily and write it like this. Voltage is equal to charge over capacitance. So voltage 1, that's the red to black voltage. I can rewrite that and call that charge over capacitance 1. Voltage 2, looking at this capacitor, that's orange to black. I can call that the charge on the capacitor divided by C2. Now this left-hand side, this voltage, remember this is the voltage across the battery, which is red to black. And I'm going to take a moment and color code over here. That's this potential, red to black. Now notice on our equivalent capacitor, red to black is the voltage across the battery. So as far as this expression, I can use this capacitor to rewrite this voltage. So that's going to equal the charge Q. I'm sorry, let me restate that. So the voltage here, which is delta V, can be written as Q, the charge on the capacitor, over C equivalent. An important fact is that this Q that we're assuming is on this capacitor is the same as these Qs, because remember what this charge means right here. This charge Q means plus Q on the left, minus Q on the right. So the charge on that plate right there is this Q. The charge on this plate right there is minus Q. And over here, that's these two plates. So the charge on this plate right there is plus Q. The charge on this plate is minus Q. So we would say that this capacitor has a charge Q, which is the same as these two charges. All right, so anyway, long story short, therefore the voltage, red to black, we can write as Q over C equivalent, the capacitance of the system. Because these charges are the same, they divide out. So basically what we have is that for a series combination of capacitors, we know that 1, all charges are the same. I'll just put the Q's are same. And 2, the equivalent capacitance of the system can be found using this relationship. And it needs to be rewritten here. Actually, I need a little room. After we divide out the charges, what we have left is 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So given values of C1 and C2, basically I would plug them in here, calculate C equivalent. All right, and I'll go ahead and do some examples a little later. So that's referred to as a series combination, and this is how we find the equivalent capacitance of the system. I'll make examples showing what we do with it later. Oh, one more thing to point out. This was assuming 2 capacitors in series. If there was a third one here, a C3, we would just have a plus 1 over C3, etc. And we could just keep going with as many of those as we need. I'm going to go ahead and just leave 1 over C1 plus 1 over C2. But because that's probably how you'll see it in the book. But again, if there's a third capacitor or a fourth capacitor, you just keep adding terms. So that's how we handle a series combination. I'm going to pause this and redraw the picture for a parallel combination. Alright folks, I'm back, and what we're looking at here is we have a pair of capacitors hooked to a battery. Now here you notice there's two branches here, that this wire comes in, branches, one branch goes to the capacitor C2, another one goes to the capacitor C1. This is called a parallel combination. Right? So now imagine when our circuit, when the switch is closed, and again, the battery now is going to push charge through the circuit. These plates are going to become positively charged, these plates negatively charged. So I've got a capacitor that I called C1. It's now going to have a charge on it that I'm going to call Q1. We have a capacitor C2. It's going to have a charge on it that I'm going to call Q2. Again, the idea now is, can I find a single capacitor that would be equivalent to this combination in parallel, right? And that's what this represents in this picture. So the million-dollar question is, how do we find C equivalent? So I'm going to start this like I always or usually do in these circuit diagrams. I like color coding the constant potential. So this is all conducting material. So this is all one potential. Remember, that was one of the I facts, important facts about conductors. So this is all one potential. On the other side, this black, this is all conducting material, so it's all one potential. I'm just going to leave it black. So an important thing to notice, red to black across the battery. Red to black across this capacitor, red to black across this capacitor. I'm going to go ahead in my picture on the right here, go ahead and color code that potential. And again, red to black. So what this is telling me is that this voltage, the battery voltage, is the same across these two capacitors and my equivalent capacitor. Right. Now, these capacitors are charged, but there's no reason to believe they're the same charge now. If I have, say, 1 coulomb of charge move across here, we might get something like 0.3 here, 0.7 here. There's no reason to believe that the charges are going to be the same. What is reasonable to say is that this capacitor is taking the place of these two capacitors in parallel. So the charge on that capacitor is equal to the sum of the charges across each capacitor individually. Now, again, remember, capacitance is charge over voltage, so this can be written charge equals capacitance times voltage. So the Q1 here, I'm going to go ahead and write that as C1 times the voltage across that capacitor, which is delta V, the voltage of the battery. Q2, that's going to equal capacitance 2 times delta V, the voltage of the battery. And then Q, this is the charge on my equivalent capacitor. This can be written as C equivalent times delta V, the voltage of the battery. And again, this delta V in the picture is the voltage red to black, red to black, red to black, red to black. They're all the same. So this voltage in this equation divides out. So over on the right-hand side now, our equivalent capacitance is quite simply the sum of the capacitances of the individual capacitors. Now this is true for two of them. If we had a third capacitor on here, we'd have a plus C3, and a fourth one, we'd have a plus C4, and so forth. All right, so at this point, we've talked about two different types of capacitances, calculating capacitance of a series system and calculating capacitance of a parallel system. Right? For a series circuit, we know that 1 over C equivalent is equal to 1 over C1 plus 1 over C2, etc. For a parallel combination, we know that C equivalent is equal to C1 plus C2, etc. It's C equivalent. Another important fact over here, getting back to the series combination, we know that the charges were the same. I guess I don't need equals. Over here, for a parallel combination, we know that the voltage across each, same. And again, I guess I don't need the equals. So that's a little bit about capacitance, what it is, charge per unit voltage, how capacitance is calculated for a series combination, and how equivalent capacitance is calculated for a parallel combination. I'm going to go ahead and make some videos demonstrating these concepts. Hope everybody has a great day.